All right. So, first we're going to go over the three fundamental constructs of lambda calculus. All right. So number one is why is this so pixelated, guys?
Because you zoomed in, I think.
Can we just make a new bigger, just double that to or triple it even. It's just gonna be a really big canvas. Jeez. Sus. Good enough.
Okay.
Alright. Number one is going to be just variables. Can I make this brush stroke lighter? Brush width 4. Is this better? Okay, that's better. So number one is variables, and I think some people they try to give it fancy 3-letter names, so you'll see it called var or something, whatever. Number two is the actual lambda. So lambda x dot we'll just say and we'll call this lam. So this is a lambda, right? And the syntax is a bit interesting, but basically this means that the lambda itself means this is a lambda, right? And everything before the dot is an argument. So x is an argument here, right? And then the actual everything after the dot is the body. And this uses the third construct. The third construct being application, and some people call this app or whatever. So basically lambdas are functions, and then you can also apply the functions.
But where'd you get F?
We'll just say F was defined else. We'll just say just imagine F is a lambda, right? So just an example lambda x x. So this is the identity function, right?
Yeah.
If you apply this on some symbol y, you get
Y.
yeah. So this is just y, right?
So basically Python app.
Yeah, sort of. And so now we also should go over what currying is, because I'm not sure if everyone's heard of this. But in lambda calculus, all functions are curried. So a function that takes in two arguments lambda x y dot let's just say this. So this takes two arguments and returns the first argument, right? This is actually just syntactic shorthand for writing lambda x dot lambda y dot x. So it's a lambda that takes in one argument and then returns a lambda that takes in another argument and returns the first argument. So there are only one argument lambdas, but you write them as two arguments to be easier. And so I guess also associativity wise, lambdas are, this is what, right associative, while application is left associative. It's f of x y is equivalent to f of x y. And then I guess
Instead of having a function that takes two arguments, think a function that takes one argument and returns a function that takes the other argument.
yes. And this is known as currying, and it also exists in programming. Haskell is entirely curried, but you can make currying in Python or JavaScript or whatever, and it's useful sometimes for partial function applications. And then I guess there are some interesting things that you can do. First, I guess we should go over this thing that I drew over here. This thing over here. Does anyone know what this is?
A lambda.
But what does this do?
It concatenates x with x. Oh wait, no. Wait. It applies x on itself. Right.
Yeah, so this is a Y combinator. I snuck that in there.
Oh, thank you.
So the Y combinator, and this is going into recursion without recursion, because normally how you would do recursion in a language like, let's just say Python, is like you define some function f, and then you now have that like name f that you can call in the body, right? But in lambda calculus, you might notice there's no way to notate like I want to call this lambda in itself, right? Like you just can't do that. So the Y Combinator is sort of this like recursive like way to do things recursively, since you are passing in the function to itself. So the function now has itself and therefore can call itself, I guess.
Wait, why can't like why is it not possible to call? Oh,
Because it's
within the
not
lambda
bound
you
to a
don't have
name.
yet.
Yeah.
Oh,
So this is sort of like, I guess, like binding it to a name. So like, um, I don't know. I guess it's like easiest to not think of it directly in terms of like pure lambda calculus, because doing operations in lambda calculus is actually this like really, there's all of this like there's church encoding in order to like actually have values, because you can represent values using only lambdas, because note there are no like concrete values here, right?
Oh, that goes back to the piano.
Yeah, I mean, there's like the church encoding of the piano naturals in order to, because you also can't do piano naturals because there are no values, there are only functions.
Oh, okay.
Um, but let's just like think of Y combinators in like uh, a language like Python, or I don't, or just some pseudo language. So let's say the Y combinator is like bound to Y. Um, so like let's just assume that this is a curried lambda. Like in Python, it would like just be this, right? To like actually explicitly curry it, but like that's too notationally annoying.
Dang, I didn't know that.
Um, so you have some like lambda that takes in itself as f, right? And then x. And then you can say like it returns let's do what, factorial? 1 if x is less than or equal to 1, else like x times f of x minus 1. And this will like actually calculate the factorial, except just kidding, no it won't, because this Y combinator will infinitely evaluate in eagerly calculated languages. So this will work in Haskell because Haskell is lazily evaluated, but this Y combinator, if you like plug it in your head, you will see that it just goes infinitely.
Right. Think about that.
So instead of calling, okay, so like in normal recursion you would call your function within your function, right? But in this case, what you're doing is instead of calling your function, which doesn't exist, doesn't have a name yet, you say my function will take in a function, which I will call inside my function.
Yes.
And then when you apply the Y combinator to it, you apply the function to itself, so it calls it itself.
Yes.
Oh, so like it's like a hack to name your function in the defining stage, like before it's
Yeah.
bound. Wow.
And
Okay.
Alex, if you want to have more fun, I believe the way to get the Y combinator to work in eagerly evaluated languages is to explicitly like write out one layer of recursion. Like is it like, I might be completely wrong about this, but I think it's something like this, possibly. Not sure.
Is that a times?
What? There's
that-
no. This is a
Oh,
dot.
XX. Oh, never mind.
I'm not sure. There's a Wikipedia article that has the actual one, but does this work if you have like? No, this makes no sense. This might be no. Whatever. It's something.
Wait, so if it's eagerly evaluated, then it'll. because it's trying to descend into f before.
I mean, I guess like we can write out a couple steps explicitly, right? Like let's just jump to the gun and call it with 0, right?
Like maybe could we like do it in actual Python?
Sure, I guess. How do you?
Let's press F12 to get a terminal.
All right, let's go.
Oh, yeah. Let's zoom in a little bit.
Oh, you have fucking iPad. It's so sad.
Okay, bring it.
Is that what Julia Utility console now?
What?
It's like, I thought Python was like the old name.
No, what?
It's like, I thought like Jupyter is like the new
I-
Minecraft.
IPython is the kernel for Jupyter notebooks.
Oh.
But there's also a CLI that is like. Anyway, you're missing out if you don't have IPython installed.
Really?
Yes, it's so much nicer. Anyway, we're gonna say like our y is just gonna be like lambda x x x, right? So this is our like hypothetical y combinator, and our factorial is going to equal y lambda f lambda. We have to do the explicit currying this time.
Yeah, we're turning this down. Why can't Python? I thought Python was supposed to be like concise. Why can't they say like LAM instead of Lambda?
All right, and let's see. Or let's not go that big. Let's just go 5. And what? Why are you like this? Unsupported operand types for. Am I trolling? I mean, x is obviously an int, and then f is going to be the function itself, and I'm dumb. This should be f of x minus 1.
Wait, what?
Or
F is itself, right? Yeah, yeah, because f is going to be f is going to be this whole lambda, which takes 2 arguments, right?
yeah, this should be this, and then hypothetically, oh wait, this just works.
Oh.
Am I trolling? What was the issue? Or is it? We're gonna take a trip to Wikipedia. Where's the? How do you? Firefox.
Wait, that hurts my brain.
What hurts your brain? Which
F
part?
wait.
Which part are you
F is.
This is. Okay, so this is. Oh, okay, sure. This is the fix for eager.
Which part are you thinking about, Alex?
So, wait, what is that?
F is the whole thing, right? Like everything within Y. So like F.
Oh wait, so okay, F is the thing that takes itself and the thing you want the factorial of.
X is the thing that you want to factorial of, right?
Yeah,
F.
so F takes itself and X.
Yes.
And then the Y combinated just gives you an F that with itself as the first argument.
Yeah.
I think the Y because we passed the lambda to the Y combinator, that's why F is itself. Because Y makes F the whole lambda. If we pass the whole lambda to something other than Y, then F could be anything else. But since we passed it to Y, and the definition Y was applying X to itself, then that makes F the whole thing.
Okay.
Anyway, so that's like sort of the Y combinator. It's kind of weird to think about, but if it makes you feel any better, this is way easier to understand than the rest of lambda calculus. So,
I think that makes me feel any better. I was so curious about lambda calculus.
I guess we can sort of go into we can go into what I know of lambda calculus, which is not a lot.
Okay, sure.
Um, so I think this is called like church encoding, but basically you want to actually be able to do things with your lambdas, right?
Right.
So you don't have values. So how could you possibly encode anything with just functions?
Why can't we just have atoms or values? Why
You
can't we have values?
you
Like,
can, right? But
yeah.
like that's sort of a like, like sort of CS lambda calculus approach, right? We're talking about just pure untyped lambda calculus right now.
Okay, but like that sounds okay. I'm sure there's like clever ways to do it, but like, is there any benefit to us not having values other than we get to
Mathematicians nut to it.
challenge?
That's the only reason. I don't know. Listen, you can like come up with whatever weird thing, and mathematicians will find a way to justify its existence. All right.
True.
Encoding values as functions.
All right. So let's just start with true and false, right? Like basic booleans, the fundamentals of information. How could you possibly encode true and false? Any ideas?
Maybe as like a parody of recursive levels.
Not sure what you mean by that.
It's like if you have no recursion levels, then it's true. If you have an even amount of recursion levels, then it's false. If you have an odd number of recursion levels, then
Okay,
it's
well
true.
you don't want to encode values as an infinite family of functions because you should just have a canonical encoding.
Okay, but like you don't have like anything to ground yourself upon because you don't have values, right?
Sure, but you have functions, right? And you
So,
can like tell functions
you
apart
can have like
hypothetically.
one as the identity function and the other one is the Y combinator.
That's like not particularly usable though, right? Like because they like take in fundamentally very different types of arguments. It's like very hard to practically use that. I will
Can we have branches in our functions?
I will write out the first part.
X, Y.
Anyone have any ideas?
Oh, so one that returns X and one that returns Y.
Yes, I believe true is the first argument and false is the second argument. So these are much easier to use because, now you can do like conditionals by like, like your boolean b and then like if true, right? It'll evaluate to this and then like if false, it'll evaluate to this, right? And like these are just shorthand for like whatever expression you want, right? It's like this is how you do conditionals with. Again, I believe this is called church encoding, but I am like very unfamiliar with this. It might not be, but
Wait, I have a question about currying. So when you currying, like, remember the add x y, right? Or was it add x y? Add x y, which returns a function that would add the number of whatever you pass as x to y.
sure.
Or maybe we can get. Oh, we cleared it, I guess. So it's like it was add x y returns. Wait. It was lambda x y. Lambda x dot lambda y dot something, right?
Yeah,
Oh, lambda x dot lambda y dot x.
yeah,
The inner lambda would have to remember x though, right? So
yes.
there's like some context surrounding it, and so like this kind of reminds me of the article that I sent in the Discord about like async and sync, and when you have async, you have to like when you pass a callback, it would have to wrap all the surrounding wrap all the surrounding context somewhere on the heap. So that's like kind of like the CS approach to it. In lambda calculus, how would the inner function know the surrounding context?
I mean, variables are bound like everywhere inside the function. It's like So there's like this terminology, and there's so much. There's like alpha renaming, beta reduction, eta reduction, which are easier than they sound. I forget which one is which, but it's like I could search it up and probably give like a coherent lecture. They're not that hard. Um, and then there's like free variables and bound variables, right? So like free variables are things that are just dangling that like are not bound. And then bound variables are anything that has been, like that
Yeah.
is an argument name in a previous lambda.
Oh, okay.
And like variables are bound for everything inside the lambda, including sub lambdas.
Okay. So when you have the lambda, that introduces unbound variable, or well, technically, like inside it would be bound, and outside to the outside it's not bound. Right?
I
If
mean,
that makes sense. So, because when you're calling it, the you can set the arguments to anything you want.
yeah.
But inside the lambda, kind of what you're receiving stuff from outside, which just has to be bound.
Yeah.
Okay.
Alex is struggling.
I'm just like, it's just like weird, cause like when you think about like context, when you think about like context within a lambda, then the inner lambda has to know the context, like the values that are its environment, right? Like its context or its environment, whatever you call it. But then like now you have to think about like memory and like all these CS concepts.
I mean, there's no, it's a pure abstract algebra lambda calculus machine. But I mean, in computer science, it's just how you implement recursion, right? Like you just push it like this same thing works in Python, like lambda x, lambda y, because x is bound for everything inside the lambda. Like it just pushes it on the stack, and then you're calling like the parent functions. Stack.
Right, it's like kind of, but yeah, you're using like CS to justify why we can do this.
I mean,
Or you're using like computer engineering to justify
I mean,
it. We can do this. Of course we can
in
do this.
math, right? The idea, like, you have to call the outer lambda to get the inner lambda. So logically, the inner lambda would have the values of the outer lambda, right? Like, or anyway, like you could. This is the intuition, right?
Okay.
All right,
It
and
is.
then let's do numbers now. Aren't they fun? Let's do
No.
0, 1, 2, what, 2, 3. Any ideas?
0 is false.
Let's start with 0.
That's true.
Then how would you do 2? Now you're out of things.
2 is 0. 2 is 1 concatenated with 0, and we're using binary.
Alex,
3 is 1
any better
concatenated.
ideas?
No.
Alright, what if I write down 0? Or, no, that's
What?
not. No,
No
no.
values, no
Yeah,
values.
just return 0. 0 is the identity function. Any ideas for 1, knowing that 0 is the identity function?
One's the Y combinator.
That's a terrible idea.
Wait, is this like going piano naturally?
Kind of. I think like I believe it's called the church encoding of the naturals, which is kind of similar to the
Wait,
piano.
let me try to figure this out. So you want like a function, wait, you want a function that will,
You want it to be usable easily, because remember, the only operations you have are calling functions with other functions.
right, lambda x s dot, lambda x s dot sx,
What did you say?
lambda sx dot sx.
This is correct, but
oh my god. I
um,
just guessed that.
I will like rename it to, or actually wait, no, this is Yeah, that should be correct. You're just calling a function on it, but we're we're gonna we're gonna rename this to f because s and x sound really similar.
Okay. Fx. Okay.
Uh,
Wait, isn't that like if you call like lambda fx dot fx with like let's say something
This over here is a list. F and x, like there's no calling happening here. This is just a list.
wait
And then here you're saying you're
like this
applying-
is equivalent to lambda f dot lambda x dot fx, or in Python it'd be like lambda. Basically, it's just a function that calls its first argument on its second.
but like wouldn't that be equivalent to like the identity function? 'Cause, like,
No, because you're spacing it out by an argument. Or wait, no, shoot.
Wait, so let's say you call like lambda
Wait,
lambda
shoot.
fx with like something g, so like
Yes.
that would be so
Wait, hold
the
on.
return value will be equal to
Yeah, I think you're right.
gx, which is just g.
Let me think. What is? There's
Like,
something
what
I'm
was
trying to.
Can you say that again?
Wait, okay, so let's say you have lambda f lambda.
Oh wait, I think okay. Sorry, 0 might not be the identity function. I think 0. 0 is supposed to be. What the?
Oh, you have to do like shift backspace.
Okay, 0 is supposed to be not the identity, but I think fx dot x there. So 0 is actually false.
Wait,
So you are taking in an unused argument.
Oh.
So
wait.
now,
so
yeah,
0 is a function that just always determined it.
yeah. So now, okay, I think this is correct now.
Wait. Okay. So 2 would be.
Anyone have any ideas for what 2 would be following this pattern?
Lambda fx dot fx.
Yes.
Oh my god. Wait. This is literally just the piano naturals, but.
Yeah, but like lambda 5.
But with 4 extra characters in the beginning.
So basically, numbers are just calling a function on an argument that number of times. It's kind of funky, but I mean you can see how this like sort of is usable, right? So like this basically lets you do like 4 loops in
Wait.
lambda
What if f
calculus.
is the identity function though? Wouldn't that make it all like indistinct?
Then don't call it with the identity function if you want to actually use
What
it.
if I want all my natural numbers to be the same?
Well, see the number like it takes in an f, so it depends on what function you give it, right? So like if you're giving it the identity function, you're basically saying I don't care about the number, which is just dumb, right? So don't do that.
Maybe I want my naturals to be.
And then the last one, because this is where like my knowledge of lambda calculus stops. Tuples. How would you encode a tuple xy? Here, I'll give you the first character.
Wow. Thank you. Thank you, Jason. Very helpful. Lambda xy dots.
How could you usably encode a tuple? And note that x and y are, just assume that they're like bound variables defined elsewhere, so you can use x and y.
Wait, so our x and y has to be arguments though, right?
No, just assume that they were bound elsewhere, like they were like already arguments like elsewhere up the chain.
So wait, x and y can either be like variables or like functions.
Well, we don't have values, so they're always functions.
Wait. Oh yeah, so basically variables are functions.
Yeah. Well, good. Remember, our values are all functions.
Wait, so the idea is that like, what do we want out of a tuple? We want it to be ordered, and we want to be able to access anything from it.
Yes.
So,
What would be a usable way to encode a tuple? We should just turn rustations into PL class.
I mean, at this point, like, first half hour was Rust, second half hour. I mean, I feel like this is so much more fun than just like focusing.
Second half hour is whatever random PL crap I learned in my free time.
Like, when did you learn all this? I'm genuinely curious.
I learned lambda calculus like when I was getting really deep into Haskell down that like theoretical
when was that?
field.
How long did it take you to learn Haskell?
To get good at it, like probably a year. I don't know.
So like in your senior year?
It was like late junior year to like early senior year. I just
wow,
went down like
that's
a
really cool.
very deep rabbit hole of like Haskell and theoretical CS.
Okay.
Okay, so it would be like, what if you just make it like a function that takes a boolean, which is like, so you lambda x, let's say.
Or well, don't use x because
Oh,
x
yeah.
is.
Okay, lambda b dot bxy.
Yes, this is a tuple because it's ordered and you can easily get any value, right? So I mean, you will see like. I mean, you will see like it should be like normally people call it f like any function. So a tuple is just calling a function like a two argument function with the values of the tuple.
How would this like I get how the numbers, right? You're calling a function multiple times, so you're getting different values out of it. Like, well, we don't have values, but suppose x had a value, then calling f multiple times would give you different values, as long as it's not like
Sure.
a binary function. But here, like, what does it mean to like have a tuple, right? Like, can you access x and y?
Sure, you call this with true, right? And so true returns the first argument, right? So if you call it with true, you get x. If you call it with false, you get y. So that lets you get elements in the tuple.
Oh wait, that's really cool. Okay.
Okay, what if you want a free element tuple?
Then you
can
just do
compose this with another
b,
tuple.
x, y, z. Or I mean, you could do two tuples or just have a 3-argument function. I mean, there's nothing stopping you from doing that. And like, it wouldn't be booleans that you're calling it with. You just call it with a 3-argument function that, as far as I know, has no special name.
Wait, this is not just a tuple. This is a list, right? Like B is like the cons, right?
I mean, you can represent lists as tuples.
Right.
Yeah, so that's like the extent of my knowledge in terms of like church encoding. I guess we could go over like alpha renaming, beta reduction, and eta reduction or whatever. After I quickly search it up because, yeah. Oh, sorry, it's called alpha conversion, not alpha renaming. Very cool. Alright, so, yeah. Alright, so, let's just go over these. Why not? Because it's, like, kind of fun. So these are, like, what the hell is happening?
Oh, you have to switch by pressing X. And then X, and then press switch again.
Yeah, I switched. Alright, let us go over alpha conversion first.
Ooh.
And so this like alpha, beta, eta crap is like all just ways to manipulate lambdas into equivalent lambdas that are maybe cleaner. So alpha conversion is entirely renaming bound variables. That is like all that it is. And so, lambda calculus, I guess you could say it has the concept of like variable shadowing. So like lambda x dot x. Like rigorously, this x is unused, and it's actually this x that is equivalent to this. So this is equivalent to lambda like x dot lambda y dot y. And this arrow is alpha conversion. So alpha conversion is literally just renaming the bound variables so you don't reuse any. That's all it is. It's not very complicated, but it has like a fancy name.
Why? Mathematicians like spend too much time coming up with these names. This is like an entire like this process is entirely when you're just writing it down, right? Like when I'm writing this on paper, I'm saying, oh, the fact that I'm erasing this and changing it to a y, this is alpha conversion.
Yeah, I guess.
It's not a computational concept. It's just like the
Yeah, because like alpha conversion and beta and eta reduction are all just ways of like converting lambdas into equivalent lambdas. Like it doesn't. All right, beta reduction. This is a really fancy term for just do the lambda, right? Like, so like the beta reduction of like lambda x y dot x and like let's say the identity function, and then like another identity function, right? You just do the substitution, and you get the identity function.
which is just x again.
What? No, because you don't. This is the upper level, right? Because like you don't. Like this is equivalent to the identity function, right? You just do the substitution. Doing the substitution is called beta reduction.
Why can't they just say do?
So it calls the first remove the other stuff as the argument.
What?
It's like simplifying.
You substitute as much as possible, I believe. Wait. The beta reduction of lambda x dot mn is n. I believe.
Oh wait. Oh yeah. Okay.
I believe beta reduction is substituting as much as possible.
Can we say so I guess like we can say like we can do this in steps, right? Like the first step would be changing this to the identity.
Yeah, the first step would then be like you do one level of substitution and you get like lambda y dot, and then this becomes substituted with like lambda x dot x, and then like this whole thing is called with lambda x dot
Right,
x.
and then this part
And
goes
then
in.
this just gets ignored and you get like lambda x dot x, right? So this is like how to do a beta reduction step by step.
Okay.
And then like eta reduction, which like I guess is actually kind of I also don't understand eta reduction like too well, but basically stuff like lambda x dot fx, this what? Oh yeah. This gets converted to just f because these are equivalent, right? Like taking in an argument and then like calling a function with it is just that. This is only valid if I think what does it say? Whenever x does not appear free in f. Oh yeah, this is only true when x is not free in f, which means that like f does not use x, right? So this is not valid if like the f function actually uses a value of x from the parent lambda, right? Like an example would be like if you have like lambda x dot and then your f function is like lambda y dot x, then you can't do that simplification because then like you would just have this part and like what is x? X is not defined, right? So if f does not use x, like if this were a y instead of an x, then this is equivalent to lambda y dot y. But like if f does use x, then it doesn't work.
Right, because f could also be a function that uses context from this.
Yeah.
Oh, wow.
And that's alpha conversion, beta reduction, and eta reduction.
Thank you, Jason. Very
And
cool.
I don't know if you want to talk about Hindley Milner.
Huh?
Do you want to talk about Hindley Milner?
Yeah, we can say that for next time.
I am actually not that familiar with Hindley Milner, but it's fine. Basically, Hindley Milner is typed lambda calculus,
Oh,
because
gosh.
all of this has been untyped,
Wait,
right?
if lambda calculus has no values, what's the point of types?
Okay, but like I think you assume that there could be typed free variables in, so this is like working with like, I mean technically you could have values in this, right? Like just have a free variable and like, but all of the operations in lambda calculus should assume no values.
Right.
But like Hindley Milner is for typed lambda calculus.
I guess variables could have types, so you don't need values to work with types. But so the point of types is to restrict your operation, right?
Well, you assign types to functions.
Yeah. So yeah. Yeah. So like I mean, at least in programming, the point of types is to restrict, like, so that you can't pass in the identity function to your natural numbers function.
Sure.
So like, maybe you could say that your natural numbers functions, your f has to be non-identity and non-periodic and stuff like that, right? I don't know.
Anyway, lambda calculus has like so much stuff that I don't know. Like Hindley Milner is, typed lambda calculus that like I believe the key thing about Hindley Milner is it can type lambdas without any like type annotations. Like
What the
it
fuck?
can the whole point of Hindley Milner is that it is able to infer the type of any lambda without any explicit typing.
That's crazy.
And Haskell's type system is based off Hindley Milner. And like Hindley Milner allows for like basically generic types, like generic functions as well.
That's
And it's
cool.
like this whole thing. And then there's also something called like System F, which is a like some like
System D.
is a typed like I don't know what being a typed lambda calculus means. Like I guess it's some set of operations that you can do that like follow the rules. Are there rules with lambda I don't know, but
There's gotta be rules to lambda calculus, right? System F. It's like system D.
and then there's the Curry-Howard correspondence, which
Mathematicians need to name their things something more intuitive. What is this? We need to stop naming things after people and naming things after, I don't know, what they represent.
something the Curry-Howard correspondence says that like these lambda calculus proofs are equivalent to actual computation. I don't know. I don't do
Curry Howard correspondence.
Math is hard. PL is hard. I don't want to.
Wait, so are you interested in PL or just cyber?
I mean, PL is kind of interesting, but like, I don't know. Most of my time is spent in cybersecurity.
That is true. Alex, what about you? Are you interested in PL?
Kind of.
Like, what's your favorite part of CS? Cyber or like AI or?
Currently it's cyber.
Is it just because Jason's?
I'm going to be judging you very harshly based on what you say next.
Curry-Howard correspondence is the direct relationship between computer programs and mathematical.
Yeah, could not be more vague.
That's wow. It's kind of wow. Mathematical proofs. I guess like what the hell? It is the generalization of a syntactic analogy between systems of formal logic and computational calculi that was first discovered. Damn, Haskell Curry got language named after him. He got so many theorems named after him.
Yeah, anyway, if you want to go over like the numerals and booleans that we covered, it's called church encoding. And I searched it up and it is actually what I thought it was called, so that's cool. And I did cover most of the stuff on this page. So I'm pretty proud of myself for
That's
that.
really cool. Thank you, Jason. This is really cool. Christian
The
code.
Church-Turing thesis asserts that any computable operator and its operands can be represented under church encoding. And then in superscript, dubious, discuss.
Damn. I guess we.
In the untyped lambda calculus, the only primitive data type is the function. Because values are for chumps.
Yep.
Yes, in typed lambda calculus, presumably you would have values, otherwise typing is kind of useless.
In 1934, Curry observes that the types of the combinators could be seen as axiom schemes for intuitionistic implicational logic. Wow, these are some big words. In 1958, he observes that a certain kind of proof system, referred to as the Hilbert-style deduction systems, coincides on some fragment to the type of fragment of a standard model of computation known as combinatory logic. Wow.
Yeah, so lambda calculus is a thing. Oh yeah, do you wanna just like a fun thing? This is like we're gonna cover ski combinatorics.
What the hell?
It's like a subset of lambda calculus, right? So you have your I combinator where IX equals X. Wow, inspiring.
Oh, is it like SKI?
Yes.
I've heard of that before. I forgot what it stands for.
It doesn't stand for anything. Well, okay, I stands for identity, K I presume stands for const, because K X Y is X, and then F X Y Z equals X Z Y Z, and basically this is Turing complete. This is provably Turing complete. That's why people care, and it's a subset of lambda calculus. So you can show that like lambda calculus is Turing complete, and I like frankly do not care. But you can construct like true and false with this with like enough effort. Well, I mean K is just true, right? And then false like what is Ki? Like Ki is like is Ki what the hell is Ki? You pass it like one value. So this is like lambda x y x, lambda x x, and then this is equal to lambda y dot lambda x x, which is the second argument. So yeah, Ki is false. So you've just constructed true and false.
Ki equal to
What?
is Ki
That's K, that's I, and then you plug it in and you get that, which is false, I think, right? Wait, am I tripping? This says false is equal to SK.
wait, so Ki is your function that always returns I.
What?
Wait.
Oh, wait, am I oh, wait. Never mind, yes, it does just always return. Wait, no. No, but then, like, if you pass in, like, a function that always returns the identity is returning the second argument. So it should be false. And I think, apparently, SK is also false, I guess. I mean, we can try it. SK is equal to, like, what, you just plug in K here? So, like, K or SKYZ, I guess, is KZYZ, which is just equal to Z. Sure, that also works. So now you've made booleans using ski.
Nice. I love skiing.
And then, like, these. Oh my god. This is like the most cursed thing ever where they made not and or, and they also like made like like an infix or.
Huh?
As in like. Yeah, so like it's just what the fuck? This is so dumb. It's like or is equal to K apparently. Wait, what? Yeah, so or is K, and you can see like if you do like F or T, right? So false returns the second argument, so this is equal to true. But if you do like true or uh, false, this is equal to so right. This is like that, and this is equal to true, right? Because it's equal to or, which is equal to true, right?
Wait, so this is. What is it? Why do you need it to be infix?
Because it's easier. You can do infix operations.
But the operation should be a function. So it should
Too
be
bad. Look at
beginning.
this infix operators in ski combinatorial.
This is the dumbest shit I've ever seen.
Don't worry. There's also prefix or. We'll call it por. Por is apparently equal to KT, where T is true, and apparently this is prefix or. I'm not gonna check it, but it's apparently true.
That's cool.
Also, Wikipedia page has postfix and.
What the fuck?
Postfix and is equal to false. So TT and is equal to true.
Oh, because false. If there's
Yeah.
a false anywhere, it'll take the second one, which will be F. If there's a false, if false is in the second
Yes.
position, then the first T will take the first one, which is F.
Yeah.
What the fuck?
Postfix and, but they also have prefix and, which is like
Okay.
equal to SSKKF, which is like yeah, sure.
I
Whatever.
guess. Okay. I'm kind of seeing the appeal of postfix and.
Postfix
When
and.
the definition is so simple that I wouldn't mind using postfix and.
So yeah, that's like more lambda calculus crap, and I I feel like this is a good stopping point.
Okay. Thank you, Jason,
Also,
for teaching us about lambda calculus.
Yeah, you should
I'll-
probably stop OBS as well.